Hello and welcome back. In this video we're working through an example where we'll compute the curvature of a helix. And we'll use a general form of a helix here with these parameters a and b that can be changed to alter the shape of the helix. So I want you to remember what these a and b quantities are doing. Here we're gonna keep them positive. They'll be both positive real numbers. And remember how these a and b work. This a cosine t, a sine t, remember if we just look at that, that's sort of the shadow of the helix in the xy plane, and that looks circular with a radius of a, so increasing a will increase the radius of that circle, the shadow of the helix. And then b affects my rate of ascent. So a higher b means I'm going to be ascending vertically faster, and what this should do is sort of stretch out the helix vertically. So higher values of B will stretch it out, lower values of B will sort of coil it up. So I just want to look at that real quick, just to kind of convince you of what I was just talking about. So here if I set A, let's say set A equal to 1, not 11, 1, we should have a circle of radius 1, right? There's that shadow. And then if I alter B, right, the idea is if I increase B, it's going to lengthen it out. And so as b goes to infinity, it's going to approach a straight line. And as b goes close to 0, we're going to wind it up. See how windy that gets? This is why I don't want b to go to 0. That's going to be a real big problem. That means we're just going to be going around in a circle on the xy plane. So I'm going to set b to 1 here. So here's our general sort of shape, and we can alter a and b. So we'd like to know what is the curvature of this space curve. So at this point, I'd like to have you just kind of guess. So write it down on a sheet of paper somewhere. Guess at what do you think this curvature is. So a couple questions to get you started. Do you think the curvature is variable with t? So depending on a point on the curve, I'll get different curvatures? Or do you think it's just a constant throughout the curve? Is it the same curvature throughout? And then 2, another thing to think about is if I increase A, will the curvature increase or decrease? What do you think? What's your intuition on curvature tell you? And then if I increase B, will my curvature increase or decrease? Those are the things to think about. So let's go ahead and jump back to, and I do encourage you to pause the video for a second and really think about that, what your predictions are for this. And now we'll go ahead and calculate the curvature of the helix. So we now have 2 formulas, right, for curvature. One, we can use this handy dandy formula we came up with here, so long as our velocity and acceleration are nowhere 0. Or we can always go back to, right, remember that curvature is 1 over v times the magnitude of dt. We could also use this one. So yeah, deciding which of these 2 formulas to use for curvature just comes from experience and thinking about what kind of quantities you're going to get out for v and a and whether it's going to be easy to take a cross product, things like this. So that really comes from experience. You can use either one and go for it. You can see if you compute velocity and acceleration, that this is going to be this hypothesis, or the hypothesis is satisfied that velocity and acceleration are nowhere 0 for this curve, for this helix. So we could use that one. I'm going to go ahead and use the derivative of the unit tangent vector formulation for curvature. So that is, I'm going to be computing curvature as an output of t is 1 over v times magnitude of dt. So that involves finding this unit tangent vector, taking a derivative of it, and finding velocity. Well, we'll need velocity to find the unit tangent vector anyway. So let's start out by just finding velocity. So we've done this, a similar one before, right? Minus a sine t, a cosine t, and b. Magnitude of velocity, so our speed. It also tells us if it's an arc length parameterization or not. Let's see, magnitude of velocity, so our speed is square root a squared sine squared t plus a squared cosine squared t plus b squared. Sine squared plus cosine squared is 1, so this is all just a squared. So this is square root a squared plus b squared. Cool. So that's my speed. So to get t then, my unit tangent vector then is, remember this is 1 over magnitude v, scaling the velocity, right? Unit tangent vector points in the direction of velocity but has unit length, so we divide by the magnitude of it. And so that's 1 over square root a squared plus b squared times this velocity vector. So minus a sine t, a cosine t, and b. Let's go ahead and compute now dt dt. This is nice that my speed is constant. So that means when I'm taking a derivative here, this is just a constant I can pull out. So I really just need the derivative of v here, and that's acceleration. So I'll carry this speed along with me because it's just constant. A squared plus b squared, right? Constant multiple. And then here I'll get, it looks like minus a cosine t, minus a sine t, and 0 there. That'll go to 0. And then let's see what's the magnitude of dt dt. Well, again, I can pull out this constant multiple. It's 1 over square root a squared plus b squared. And then times square root of, so magnitude of this vector, so that's a squared cosine squared t plus a squared sine squared t. It's got no z component, so just 2 terms here. That's really just a squared. I'm assuming a is positive, and so square root of a squared is just a. And so what we get here is a over square root a squared plus b squared. So that's magnitude of the derivative of my unit tangent vector. And then curvature, so now we can plug all this in like I always recommend, get all your pieces together and then just plug them into the curvature formula. So 1 over v, so that's 1 over square root a squared plus b squared, and then multiply that by magnitude of dt dt, so that's a over square root a squared plus b squared. And that has a nice, right, that breaks down nicely. That just turns into a squared plus b squared. So we have a over a squared plus b squared. So some things to notice here. This is great. We got our answer. That's the curvature. Some things to notice and compare to your hypotheses at the beginning of this, or your predictions of what was going to happen. This is constant. So at any point on the curve, it's the same curvature. Some other things to notice, as b increases, as b goes to infinity, and just as b increases, the curvature will go to 0. And same thing with a, right? We have a on the top and an a squared on the bottom, so this is going to act like 1 over a as a gets really, really large. So as a goes to infinity, k also goes to 0. So if we increase either a or b, the curvature should go down. And this, right, so this should inform your intuition. Hopefully you had that intuition already and guessed that this was going to happen. But if you didn't, that's totally okay. This should now inform your intuition. Your intuition should now become stronger that you've encountered this, right? So why is it that when I increase a, so I'll start here at a equal 1, as I increase a and keep b fixed, right, it's widening. It's not turning as fast. Think about how the unit tangent vector moves. If a is really, really small, even less than 1, it's going to be turning really, really quickly when I increase t, compared to if I widen it. Same thing for b, right? b flattens this thing out. So if I let B get really, really big, it's almost acting like a line. And that's the idea, is it should be sort of in the limit acting like a line, and a line has curvature 0. So that's the idea here. And we have our answer, and we've increased our intuition a little bit about curvature, hopefully. So a nice calculation here. That's it for this video.